Hello everyone, thank you for checking out this particular video. This will serve as the practice exam review for Math 1325, Math 1425. For those of you that don't know what that is business calculus, first exam. So I'm making this video in an attempt to be able to thoroughly explain the concepts that you'll see on your upcoming exam. For those of you that are not taking my course for whatever reason, this may still help you in your respective business calculus exams for your first test as well. So hopefully something that you see in here will be helpful to you. All right, so let's go to our first question here. So first question talks about how to describe in words and by using pictures the ways that there can fail to be a derivative at points on a graphical function as you're shown in your text. And so in general here, we know that whenever we're taking the derivative of a function, we know that we're trying to do the limit of the difference quotient. And so I'm going to go back a bit to sort of explain why the answers that we're going to have are what they are. So one of the things that we know whenever we take the limit of a function just in general is that when we say the limit as x approaches a of f of x, what we really mean is this. The behavior of that function coming from the left side is the same as the behavior coming from that function from the right side, and that has to equal some real number L. Okay, so that is what that means. Now, in terms of the derivative, we're actually doing the limit of the difference quotient. So when we say this, of course, this is one form of the difference quotient. What we also mean is that the limit as h approaches 0 from the left is going to be the same as the limit as h approaches 0 from the right. And so what this is communicating to us is that if we're trying to find the instantaneous rate of change of a function at a particular point, which is what the derivative of a function actually is, then we're saying that the rate of change coming from the left of wherever that x value is and the right of wherever that x value is acting the same. Okay. Now, so that means the rate of change coming from both the left and the right have to be consistent with one another. Okay. Now, because of that fact, there are a couple of different places where that fails. And so what I'm going to do now is erase this, and we're going to list those and draw examples of those graphs, and then we're going to see why in each case it fails to have a derivative. All right, so the most simple case would be a corner. And so to have a corner in a graph, let's say we have some function that kind of looks like absolute value here, but in this case it's going down. And so we see, particularly at this point here, we cannot have a derivative. Reason being, if we look to the left of when x is equal to a, the graph looks as if it is increasing. If we look to the right of x equals a, then the graph looks like it's decreasing. And of course, we're reading from left to right. If we look exactly in the middle here, then it looks like it's constant. And so the thing is we have to have consistency coming from all sides. And so since there is sort of this state of quandary of, all right, well, from the left it's doing one thing, but from the right it's doing another. And when I'm sitting exactly on top of the mountain, it looks like I'm there. You have all three things going on at the same time. And so it's impossible to determine what is happening exactly at x equals a. Now, to the left of x equals a, our graph is increasing, which means that when we're trying to take the derivative of points on the line of that function, they are positive, okay? And of course, to the right of x equals a, the graph is decreasing. So that means the derivatives of the slope of the tangent line, which is another way of interpreting the derivative, would be negative at that point, okay? So that's why the corner is one of these examples. Now, the next one is end of domain. And so for that one, this will be something simple like here. And I'll just put some value x equals a there. So in this case, do you remember how we talked about the limit of some function as x approaches a has to be the same as the limit from the left as it is the same as the limit from the right? So in this case, the problem is when we're trying to take the limit of the difference quotient, we do have something going on to the left of x equals a, but you see to the right of x equals a, our function is not defined. So since it's not defined, we cannot define the average rate of change either. And thus, since we can't find the average rate of change because we have nothing on the right side, we also cannot come up with an instantaneous rate of change by doing the limit of that, okay? So that's why end of domain is another answer for this. Now, the next example that I'm going to do is what's called a continuity. And in particular, I'm going to do a jump discontinuity. So if we look at this graph here, I'm going to do something very simple. So let's say we start off like this, come down with an open circle, and come up here and go like that, again at x equals a. So in this case, we see that to the left of x equals a, it looks like the rate of change of the function is, possibly going towards 0 or maybe a very low negative number. Whereas to the right, it is a positive number. But regardless, because we have this jump discontinuity here, the behavior from the left is not the same as the behavior from the right. And so the slope of the tangent lines coming from the left and coming from the right aren't consistent either. And so that's why we actually fail to have a derivative there, okay? And so that's a good reason here to know why when we have functions that aren't continuous, we can't actually find a derivative there, okay? Now, the same thing would hold true if this were, instead of a closed circle there, we would have an open circle here and then do like that. Of course, it would still be the same thing, okay? Now, of course, one of the conditions for a function having a derivative at a point, which is understood, is that the function actually has to have a defined point there. So in this case of where we have the two open circles there, we can't even consider that because there's not a defined point there. Because the two main things that have to come together for you to be able to have a derivative is you have to have the limit of the difference quotient exist, and you actually have to have a defined point at x equals a, which brings along the continuity piece to it. So that's one of the reasons why when you're studying calculus, you go through the whole thing of learning what a limit is, and then after that you learn this basic fact of continuity, which says that the limit at x approaches a of f of x is equal to f of a. You have to have both of those things in place to be able to define a derivative. And just to make sure that you understand about continuity, this one statement actually has three phrases in it. And the first phrase is that f of a is defined. And of course, what that means is you actually have a point a, f of a on your graph. Number two, you're saying that this limit here actually exists, meaning that when you get an answer for that, is actually going to equal a real number. And then the third thing, what you're saying is actually what this says, which is items 1 and 2 are actually equal to one another. So that means the behavior, which is how we interpret the limit, the behavior of a function as x approaches a from both the left and the right equals some real number, and that real number is the same as f of a. So you're saying f of a is going to equal to L, okay? So we need all that to be able to come up with a derivative. And so that's why here for the case of the jump discontinuity, whether we have a closed circle here or not on one of these, we still can't find a derivative there. All right, so we have two more cases here. Another case would be what is called a vertical tangent line. And of course, a good example of that would be looking at the function cube root of x. So I'm going to try to draw it here. So cube root kind of looks like that and then goes there. So here at this particular point, when we're imagining that that's vertical there, the slope of the tangent line exactly at that point, if imagine that it's vertical, would be infinity. Okay, so kind of like a vertical line. Vertical line, its slope is infinity. Now remember that whenever we talk about the derivative of a function, it is the limit of the difference quotient. And regardless of what we're taking the limit of, in order for the limit to exist, it has to equal some real number L. If you notice, infinity or negative infinity, depending on how you want to look at it, if you're coming this way, does not equal a real number. Infinity is a concept, not necessarily a number. So that's why in this case, anytime you have some odd nth root, like cube root of x, where that function actually equals 0, in this case, would actually be a point where you have a vertical tangent. Okay. All right, so let's move on to the last example, or the last answer to this question. All right, so the last answer to this would be what's called a vertical asymptote. Of course, vertical asymptote, an example of that would be something like this. And we see these a lot in our rational functions. So let's say at x equals -2, we have a vertical asymptote. So let me try to do this here. So let's say our graph actually goes like this on this end, and then it comes down like that and kind of does like that on that end. Okay. So that would be an example of a vertical asymptote. Basically, it's another discontinuity, but it's a discontinuity where the actual line where the discontinuity is sort of acts like a wall. So the function either tries to go above it or below it. And if you notice, if you look at the behavior of the function coming from the left, it's different than the behavior of the function coming from the right. And so we have two inconsistent things going on. So the rate of change to the left in this case is going to positive infinity. The rate of change coming from the left is negative infinity. And of course, in both of those cases, we still have some limit equaling either positive or negative infinity, which is not a real number. So we can't consider that. Another example of a vertical asymptote where the behavior looks like it's the same, but we still can't say that we actually have a derivative there would be something like this. So let's say this is at x equals 1, and now our function kind of goes like this, where as we approach x equals 1 from both the left and the right, we see that the function goes to infinity either way. So that means the behavior of the function itself coming from the left and the right is such that it's going to infinity. But again, when we have the limit of the difference quotient equaling infinity or negative infinity, that's still not a real number. So we can't have a derivative there by definition. And so that is the reason why for questions like this, where we're asked to describe either in words or pictures, the ways in which a derivative can't happen, these are all those cases. All right, so let's move on to question number 2. All right, so for this question, we're asked to take some function r of w and basically calculate the derivative of it and evaluate it at 1. So to interpret this, what we're wanting to do is find out what is the instantaneous rate of change of this particular function at x equals 1. Or put another way, we want to find the slope of the tangent line of this particular function at x equals 1. Now for here, all that we're being asked to do is to actually compute it. So we just need to use our derivative properties. So the first thing that we need to do is just figure out what R of W is. So we notice that we have two terms in our function, and both of them end up being either power functions or linear expressions. Now, the first thing that we want to take care of is our second term. We see that we have 9 squared here. 9 squared is just a number, and it's just 81. So what we're really dealing with is we need to take the derivative of 4w raised to the 9 minus 81w. So when we take the derivative of this, we're just going to use the power rule for the first term. And so to do that, we know that our coefficient that's on the outside, we're going to take our exponent 9, multiply it times that, and then per the power rule, we're going to subtract 1 from the exponent. For the 81, if you look at this conceptually, whenever we look at the function 81w, that's like saying 81x. And of course, that would be like a line, and the slope of that line would be 81. And so hence why the answer to the derivative of 81w is just 81. But if we use the power rule, we'll see that we get the same thing. And so of course we have an understood exponent 1 here, and then we just say 1 minus 1 for the exponent. And so this is 36 w raised to the 8 minus 81. And of course, w raised to the 0, that is the same as just 1, because anything raised to the 0 power is 1. So our final answer here is just w raised to the 8 minus 81. And so that is what we get for the derivative of r of w. So now all we have to do is evaluate this function at 1. And so, of course, using order of operation, 1 raised to the 8 is just 1, and 1 times 36 is 36. And so then from there, if we do 36 minus 81, we get a negative 45. And so that would be the answer to this particular question. All right, so let's move on to question number 3. All right, so in this question, we're asked to calculate the derivative of a function w of n, where n is our independent variable and w is our dependent variable. So that's important to us here because if we do not see anything written in terms of n, then that means that it is a constant number, or it's just another variable that we don't know what it is, so we're going to treat it as a constant. So notice in this case, our function w of n has logarithms in it. And so since it has logarithms in it, the best way to be able to take the derivative of this is to actually simplify the logarithms as much as we can, or rewrite it to where when we actually take the derivatives, we're taking the derivatives of just natural log of something. And so by doing it that way, it makes taking the derivatives much easier to do. So let's start off by trying to simplify as much as we can here. So we know that natural log of e is just like log base e of e, which turns out to be 1. Okay, so we know that much. So we got 1 plus 2 times e raised to the n, and so we'll leave this alone. But here, do you see how we have natural log of 4 times n? And so one of the things that we know from our logarithm properties is that if we do log base a of x times y, that's going to be log base a of x plus log base a of y. And so where this actually comes from is its equivalent within the exponential world. And so this is essentially what we're saying here, that anytime we multiply a two exponential numbers that have the same base, we can add the exponents. If you remember, the logarithm is just the inverse of the exponential function. So what a logarithm actually is just a fancy way of expressing the exponent of an exponential function. So here, this is why when we switch this property from exponential form to logarithmic form, this is what it looks like. Okay? So in knowing that, we could rewrite this as natural log of 4 plus natural log of n. And if you notice, I put all this inside a grouping symbol to know that even though I'm expanding this out using my logarithm properties, I have 2 times e raised to the n minus all of it. And so I'm doing this to remember that I need to distribute this subtraction sign or negative to both terms in my next step. So I have this, so I distribute and I have that as a result. So now this is what w of n actually is in a little bit more simple form, okay? So now when we figure out what the derivative of w of n is, whether you want to write it in prime notation or if you want to write it in Linus notation, then we know that the derivative of any constant is 0. So the derivative of 1 is 0. Since we have this constant multiplied times e to the n function, we can just write that, and we know that the derivative of e to the n is just e to the n, just like the derivative of e to the x is just e to the x. So from there, minus, we know the derivative of natural log of 4 is going to be 0 because natural log of 4 is just a number, okay? If you type that into your calculators, you'll see that you actually get a number. Please do not make the mistake of saying that the derivative of this is 1 over 4, because that's not correct. But we only do that whenever we have natural log of some variable, like in our last step here. So natural log of n, the derivative of that is just 1 over n. And so now, once we simplify everything, we get 2 e raised to the n minus 1 over n. And that is what the derivative of this particular function is. And so to do this problem, you must remember your logarithm properties, and you must remember your derivative properties or your differentiation rules. Okay, let's move on to question 4. All right, so for this one, it says find dy for the function, and this really should say y equals 6 divided by square root of x. So I'm just going to rewrite it here. And the first thing I'm going to do, since this has something to do with the derivative, I'm going to rewrite all this in a way where it's easy for me to take the derivative. Now, first thing that I know is that I could rewrite this way. And I know that square root of x, if I write it from root form to exponential form, would be the same as x raised to the 1/2. Let me try to get that looking a little better. So that's x raised to the 1/2, which here 1 over x raised to the 1/2 is the same as x raised to the negative 1/2. So that is what our function y would look like. Okay. Now, to give you some perspective on what this actually is, I'm going to go through some background information and then go through the calculations. Okay. So in general, we know that whenever we're dealing with a derivative, and let me start off writing it this way first. So let's say we say y prime of x, then we know in terms of limits that would look something like this. And I need to change this to make that look more like what it's supposed to. Okay. So here what we're saying is we want to do the limit, or we want to study the behavior of the change in y values over the change in x values as the change in x values go to 0. And so if you remember here, change in y over change in x is just a fancy way of writing the slope of a line. And the connection here is that if we had 2 points labeled x1, y1 and x2, y2, and we wrote this first point as just x, f of x, and then the second point in terms of x would be h units away from that, then that second point's x coordinate will be x plus h, and then the corresponding y value would be f of x plus h. And then you would see that after we do all of this, our result would look very much like our difference quotient here. And of course, the x and the minus x cancel to be 0. So when we cancel all that out, we just get h in the denominator. So I'm saying all that to say that whenever we find out the actual derivative of a function y with respect to x, in terms of derivative, that's what all this means. And when we write dy over dx equals y prime of x, this dy, what we're saying in this case is we're taking the smallest change possible within y with respect to the smallest change possible in x. So just think of, just saying, all right, if y is 1, then the smallest change possible that you can think of is 1.000. You got like a million zeros after that, and then a 1, okay? And then let's say the current x value is 2, and then the change in that x value, let's say, is going the other way. So it's 1.99999, about a million nines, and then 8765, something like that. So if you see, there's a very, very, very small change in the y value, very, very small change in the x. And so when we see dy here, what we're actually trying to do is get a good approximation at worst, but at best, get an actual formula for what is going to be the theoretical formula to be able to figure out what is going to be the smallest change in y theoretically possible. So that's what's actually going on here. And we're actually going to use this concept in another problem where we're asked to find the differential. And what the differential is you're wanting to use this relationship to be able to approximate a change in a particular variable, okay? So all we're doing now is just getting a formula for that. So I'm prepping you with this so that later on in the video, when we go over that particular problem, you'll kind of already been exposed to it if you didn't notice that before. So now that we have this part, this is pretty much all we need to be able to do what we need to do for this problem. So here, we just want to solve for dy, which is the smallest infinitesimal change in y possible. If we multiply both sides of our equation by dx, then we just have dy equals y prime of x times dx, okay? And so from here, all we're asked to do is to take the derivative of y with respect to x, which we have here, and then multiply it times dx for our answer. So if we take the derivative of 6x raised to the 1/2, then of course, we know we have 6, that's the constant that we can pull out. Since this is written in terms of a power function, we could multiply 6 by negative 1/2, and then after that, we would have to subtract 1 to it. But since we have a fraction here, we're going to write 1 as 2 over 2. And so then from there, we know that 6 times a negative 1/2 is just a negative 3. And then this will be x, who forgot something here. Yeah, I need to put my dx on the end there. So sorry about that. Got a little ahead of myself. So we're going to do all of this for the derivative, and then we have to multiply it times dx. And then from here, we have negative 3x raised to the negative 3 over 2 dx. And of course, at this point, you're fine with leaving the answer that way. But one of the things that's common practice is whichever form that your function was given is the form that you want to give the derivative in. So for here, we see that it was given in root form because we have a square root of x and therefore y. So we're going to change this back into root form. And if we do that, that would just be negative 3 divided by square root of x cubed. So that is what that would look like when we put it in root form. Okay? And just in case you may have forgotten the power rules, we know that, well, switching everything from a fractional exponent to a root, we know that this is the relationship in between. Okay, so when we look at the x raised to the negative 3 over 2, of course, we know that anything raised to a negative number is just 1 over that with a positive exponent. And then, of course, after that, we use this particular property to change basically 1 over x 3 over 2 to square root of x cubed. And, of course, that'll be 1 divided by that. So that's how we get that particular answer there. All right, so let's move on to question number 5. All right, so for question number 5a, we're asked to evaluate each limit using the graph of the function below. And so when we're asked to evaluate a limit, what we're really studying is the behavior of the function. And so if we just have something like an example 8, where it just has the limit of the function s of t as t approaches negative 2, then what that means is, what is the behavior of s of t as t approaches negative 2 from both the left as well as the right? And if your graph looks as if it is going towards the same y value, it doesn't necessarily have to be defined at that y value. But if it looks like it's going towards a particular point, whatever that y value would be, that is what the actual limit is. Now, if you have a situation where the way that your graph is behaving is such that the behavior from one side is different than the behavior from the other side, then the solution to that would be does not exist. So I'm going to give you a quick example of that before we start answering. So here, remember when I had drawn a graph like this before. And so let's just say this is at x equals 3. So that's y, let's make that x. So here, we know, let's say at this point here is at 4, and this one here is at negative 1. Then here, if we said the limit as x approaches 3 from the right of this function, the answer to that would be negative 1. Because coming from the right, which is this way, we have this graph here, or this piece of the graph. If we did the same thing, where we're approaching 3 from the left, now the value is 4. But if we ask this question, which is, what is the behavior coming from both the left and the right, even though these two are equal to real numbers, they're not the same real numbers. So in this case, we would have to put does not exist, okay? Because the behavior coming from the left is not the same as the behavior coming from the right. So with keeping that in mind and knowing also all of our places where if we don't have something both coming from the left and from the right, we would have to say it doesn't exist there either, we can answer these questions. So for this first one here, if we look at our graph of s of t, here when t is negative 2, if we look from both the left and the right, we see that the behavior of the function is approaching a y value of 1, since we do have a defined point -2, 1 there. Okay. Now, again, this function does not have to be defined at x equals -2 for us to still be able to answer it with 1, because it's how the function is behaving, not necessarily what the y value is. Okay. Now, let's look at B, and maybe this will illuminate my point. When we say the limit of s of t as t approaches 1, or put another way, what we're asking here is what is the behavior of the function s as t approaches 1 from both the left and the right. Okay. The answer to that question, again, is 1. Some people may want to put the answer as 0 since you see this jump discontinuity here and you have defined point here at 1, 0. Now, it is true that s of 1 is equal to 0, but that is not what question B is asking. It is asking what is the behavior of the function as t approaches 1 from both the left and the right. And you see that both from the left and the right, that function looks like it's approaching the y value of 1, even though at exactly when x is equal to 1, the actual y value is 0. Okay? So that is the difference in between behavior versus what it means when you're actually trying to figure out, well, what is the y value for the function when x is whatever. Okay? All right, so let's, oops, sorry about that. Let's go back up. Whoa, what happened there? Okay, all right. Sorry about that, y'all. So for our next one, we see here that we have what is the behavior of the function s of t as t approaches -3 from the right. Okay. Now, if we're looking at -3 here, from the right is looking at it this way. And so from the right, we actually do have a function here. And we see that as we continue to get closer and closer to x equals -3 from the right, the y value is approaching -1. Okay. Now, to make my point here, if I would have asked you this question, what do you think the answer to that one would have been? Well, if you say it does not exist, then you're exactly right. Because here, do you see to the left of x equals -3, our function is not defined. And so since it's not defined, we have nothing to compare it to. There's no behavior to study. So that's why the answer to that would be does not exist. Okay. All right, so let's look at the final part to this, which is part D. The limit, or put another way, the behavior of the function s of t as t approaches 4 from the left. Okay. And so if we look at our graph here, if we see at x equals 4, our function is not defined at all. So since our function is not defined at all, the answer to that would be does not exist, because there is no behavior to study. Okay. All right, let's move on to question 5b. All right, so for question 5b, we're asked to identify all values of t for which the function s of t is continuous. And so if you remember, general definition for continuous is the function cannot have any breaks, holes, gaps, or discontinuities of any type. So every place where we see a hole or a jump discontinuity or the end of a domain or a vertical asymptote or something like that, then we know that the function is not continuous there. All right, so looking at our values of t here, of course, we know that at -3, that's the end of a domain. So of course that function can't be continuous there. So we would have to do parenthesis -3. And then we keep on going until we see our hole here. So at our hole, that's located at t equals -1. So we have to exclude t equals -1 from the t values that are continuous. And so this is how we skip it. We'll keep on going until we get to 1, because again, we have a jump discontinuity here. Then we skip that. And then of course we keep on going to when x is, sorry, not x, but t is equal to 3. And of course, since that's the end of the domain, we have to put parentheses on that. And so that is how, or these are the values of t where the function is not continuous. Oh, sorry, is continuous. We know that it's not continuous at -3, -1, 1, and 3. Okay? All right, so let's move on to question 6a. All right, so for this question, we want to identify the end behavior of the function f of x. And of course, we see we have some rational function there. And then we want to explain or show our work. So here in calculus terms, how we show the end behavior of a function is we ask ourselves, what is the limit of the function as x approaches positive infinity, and what is it as x approaches negative infinity? Okay. Now, for this question, we actually have a hard way and an easy way that we can do it. I'm going to do it the easy way by using background knowledge that we already know. And then I'm going to work this out the long way so that you can see how it would actually work out. The answer to this question, just by looking at that rational function, would be the end behavior is going to be as x approaches infinity, y is going to approach 1/3. And that's both as x approaches positive infinity and as x approaches negative infinity. We know that because from college algebra or pre-calculus, depending upon what course you took before you took this one, we know that whenever we have a rational function, and a rational function is simply just a polynomial fraction, where we have a polynomial in the numerator and a polynomial in the denominator, where the denominator is not equal to 0. So if we have that set up like how we do here, then we compare the degree of the numerator versus the degree of the denominator. And so the degree is just the highest exponent on any variable in our numerator and denominator. So here our degree is 7 in the numerator, degree is 7 in the denominator. So they are equal. So according to what we learned in college algebra or pre-calculus, we know that when the degree of numerator and denominator are equal, we take the leading coefficients, and of course there's an understood 1 here. We take the leading coefficients and we divide them. And that is how we figure out what the horizontal asymptote is here. And of course, a horizontal asymptote, by definition, is what happens to the function for very large values of positive x and or negative x, such that the function's behavior is going towards some specific y value. Okay, so here, to try to draw this to make it a little bit more understandable, we don't know what's going on with the rest of this function, but we do know at y equals 1/3, our graph, either coming from up this way, is going to start to ride along this graph here, or it may come from down here and up like that and ride along that horizontal line y equals 1/3. And of course, it may do the same thing from this side, coming either way. So that is what the end behavior is. So one way to describe this is as x approaches positive infinity or x approaches negative infinity, corresponding y value or f of x is going to go to 1/3 either way. Okay. Now, if we were in pre-cal or college algebra, this is how we would do it. In calculus, whenever we talk about the behavior of a function, we put everything in terms of limits. So the answer to this question would be like this. The limit of f of x as x approaches infinity or x approaches minus infinity, in both of these cases would be 1/3. And so this is all you need to put for the question. okay? Now, what I'm going to do is erase all of this and actually work it out computationally so that you'll see that even when we, do it algebraically instead of conceptually, we still get the same answer. All right, so one way to work this out computationally, and I'm just going to do the limit as x approaches positive infinity, so this won't get too long, is depending upon what text you have, your text will say, if you have a polynomial here, then the behavior of the polynomial as x approaches positive or negative infinity acts a lot like the leading terms. So you'll see this. And so I'm just going to write f of x here instead of writing all this out. Here, what we could do is rewrite this way. Okay? And of course, from there, we know that the x raised to the 7s will reduce to 1. And all that we have left after this is 1/3. And of course, the limit as x approaches infinity of any constant is just that constant. And so that's how we would get 1/3. And of course, if I did as x approaches negative infinity, I would get the same answer. Okay. So for those of you that have the text that sort of say that, where they just do the whole thing of reducing to what the leading coefficient is, that's how you would work that out. For those of you where you have the text where we actually have to work this out a little bit in more detail, I'm going to go through that example now. All right, so this is what it looks like if we actually evaluate the limit computationally. And so we start off right here by saying the limit as x approaches infinity of this function here. And notice what I do is I multiply our function here by 1, but I make 1 look like 1 over x raised to the 7th divided by 1 over x raised to the 7th. And the reason that I'm doing that is because of this particular theorem above. And so this theorem says that anytime when we have a rational function of this ilk here, 1 divided by x raised to the r, where r is a rational number, if we take the limit of that as x approaches infinity or negative infinity, then this function goes to 0. And of course, this makes sense if we go back and remember what the graph of 1 over x looks like, our reciprocal function. And so our reciprocal function kind of looks like this. So as x approaches infinity, the y values are approaching 0, both coming from the right and from the left. And with the square reciprocal function, which is just if we, I'm going to redraw this here. So if we do 1 over x squared, then the reciprocal function kind of looks like this. And so as x approaches positive infinity or negative infinity, it still tends to go towards the y value of 0. It never gets there, but it still goes towards that. So that's where this particular theorem comes from, and that is the reason why I'm doing this to start off with, so I can get all my terms in that form. So once you see that I multiply 1 over x raised to the 7th to both the numerator and the denominator, I get what you see here in the second step in the numerator and in the second step in the denominator. Okay? So the next step after that, we come down here to the bottom, I am just simplifying. So I know that x raised to the 7th divided by itself is just 1. For the second term, we have x in the numerator, x raised to the 7th in the denominator. So we know that a pair of those x's will reduce to 1. And then, of course, in that last term in the numerator, we don't have anything to reduce. We just keep it as is. And, of course, we do the same sort of similar thing in the denominator, and we get 3 minus 5 over 6x minus 21 over x raised to the 7th. Okay? Now, notice that I have kept the limit notation all the way through until I actually apply it. I am saying this because on your exams, you must use the limit notation properly to be able to get full credit. if you just kind of just write stuff and then you stick in an infinity whenever you want to, or just leave out the limit notation altogether, you're probably not going to get full credit for that, okay? So the limit notation is just like any other notation. It has to be used properly, and there is not an option on whether you need to write it or not, okay? You need to write it. So I want to make sure that we're clear on that, because every time you're saying that, you're communicating something to the reader. So when we jump from this step to this one, what we're actually communicating to the reader is that, yes, I'm actually applying this particular theorem in this next step. And so that is why here I'm plugging in infinities everywhere where I see x. And then I know that any number divided by an infinite number is always going to approach 0. And so that's what this theorem is saying here. So that's why you see all 4 of these terms reduced to 0. And of course, all we have left that's not 0 is 1 in the numerator, 3 in the denominator. And that's how we get 1/3 as the answer here. So if we were going to do this computationally, that is actually how you would do it. And if you're taking this course and your instructor actually wants to see it this way, you need to ask just to be sure. But if your instructor wants to see it this way, then at least now you have a frame of reference on how to go about doing it. All right, let's move on to question number 7. Yep, sorry about that. We need to go to question 6b first before we go to 7. So here we have the same type question, but now we see that our our rational function looks different. Now we see that the degree of the numerator is different than the degree of the denominator. And matter of fact, the degree of the numerator is smaller than the degree of the denominator. So from what we remember from college algebra or pre-cal, we know that whenever the degree of the numerator is smaller than the degree of the denominator, then we know that we have a horizontal asymptote at y = 0. And of course, in this case, in terms of end behavior here, the horizontal asymptote is the thing that is telling us about the end behavior. So simply put, we'll say the limit of f of x as x approaches infinity. Here, since this is a rational function, could be the same as the limit as x approaches infinity of x raised to the 7 over 3x raised to the 8th, if we use the leading coefficient or leading term approximation principle there. And so, of course, when we keep on doing this, we'll see that x to the 7th and x to the 8th, both of these have 7 x's that are multiplied times each other. So when we reduce all of that, here, that's just going to go to 1, and this is just going to go to x. So we just have 1 over 3x left. And then at this stage, when we plug in the infinity, we know that our denominator is going to simplify to infinity, because 3 times infinity is infinity. And anything divided by infinity is approaching 0. And so that's why our answer is 0 there, okay? And of course, if we did the same thing with negative infinity, we would get the same result. The only thing different, if we had x is approaching negative infinity, at this step here, we would have 1 divided by 3 times negative infinity, which would be this. And of course, 1 divided by negative infinity still is going to approach 0. Okay. All right, so let's go ahead and move on to question number 7. So what question number 7 asks us to do is we want to sketch a graph of the function given information about it. And so we're given information about this function in terms of limits. And so like how we've said before, anytime we discuss the limit of a function, what we're actually doing is describing the behavior of it. So we want to look at each of these, interpret what that behavior is trying to tell me, and then from that we're going to come up with a resulting graph. Please note that the graph that you come up with may be different than the graph that I come up with, but all these properties here, A through E, have to be shown in that graph. That's the one thing that cannot change. okay? Or they cannot be different, I should say. All right, so for A, we're saying that the behavior of the function s of t as t approaches -2 from both the left and the right must actually be 2, okay? So that means here, as t approaches -2 from both the left and the right, the function has to look like it is going towards a y value of 2, okay? Now, if you notice here for E, notice how this says that s of -2 does not exist. So with A and E together, what they're trying to communicate to you is that your function actually has a hole at the point -2, 2. Or put another way, when x is equal to 2, we know that y would be equal to 2 if the function was defined, but this will have to have a hole right there, okay? Now, besides that, you can do just about anything else you want to with this graph. So what I'm going to do is kind of go like this, and then go up like that. And then for here, I'm just going to say, I'm going to go like this for right now, because I don't know what else I'm going to have to do. So as of right now, all we know is that we're going to have a hole, okay? And A and E take care of that. So we're done with those two. Now let's go to B. B says that for our function s of t, the behavior of it as t approaches 0 from both the left and the right does not exist. So what that means to you is that this particular function, when we take the limit of it at t equals 0, it will not equal a real number. Okay, that's what that means. So, or the other interpretation of that is that the limit coming from the left is not going to be the same as the limit coming from the right. So if they do equal, the limit from the left equals a real number and the limit from the right does not equal a real number, then what that means is those real numbers are not the same. So to put that plainly on how you need to draw this, I would suggest that for part B, you either A, draw a jump discontinuity at t equals 0, or B, draw a vertical asymptote at t equals 0. I am going to choose to draw a jump discontinuity just because I think that would be a little bit easier for me to do, okay? So what I'm going to do here is I'm going to kind of draw something like this, and I'm going to do a closed circle here. And I'm going to go ahead and try to connect all this together, and then I'm going to do an open circle right here, okay? So I know the behavior of the function coming from the left is not the same as the behavior of the function coming from the right. And I think I may just kind of jet this out like this for right now, okay? All right, so B is now taken care of. For C, this says that the limit of the function, or the behavior of the function s of t as t approaches 1 from the right, has to be 0, okay? So we're coming from the right here, and it has to be 0. Now again, there's several different ways I can do this. The easiest way that I could do this is I could just make this point defined here and kind of go off with my graph like that. So no matter what else I have going on, I know that at t equals 1 coming from the right, it's approaching 0, okay? Now, to kind of make this connect, what I'm going to do is take this part off, and I'm going to make my graph kind of do like this. Oops, it didn't quite go the way I wanted it to. I'm going to kind of start here and connect it that way, and then come and connect it like that. So we see that what I've actually drawn is that the behavior of the function as t approaches 1 from both the left and the right are going to a y value of 0. But as long as I satisfy it from the right, that's all that matters, okay? So we have C taken care of. Now let's go to D. D says the behavior of our function s of t as t approaches 3 from the left is going to be -1. Okay. So here what I'm going to do is I'm going to do a hole right here, because that's what I'm choosing to do. Don't have to do that, but I'm going to do a hole right here and kind of make sure my graph goes like that, such that, that's not looking good. So let me try from here. So basically I want something like this, okay? So that as we approach t equals 3 from the left, it goes to -1, okay? Now what I'm going to do, I'm going to do a jump discontinuity and start down here and then just kind of go like that. And so that way I don't really care about what's happening to the right. So I can, put anything I want to the right, but I know to the left it has to be approaching -1. So that's what I have. So this is an example of what you need to have. Now, of course, your graph, if you do this on your own, it may look different, but the one thing that must happen is you must have a hole right here. You must have some sort of discontinuity at t equals 0, whether it is a jump discontinuity like how I have here or vertical asymptote. You must show that your function is going towards the y value, y equals 0, to the right, or as the function approaches 1 from the right. And so you could either have this as a defined point, which is a closed circle, or you can have it as an open circle. That doesn't matter. But as long as you show that that function behaves like it's going towards y equals 0, coming from the right of 1. And then of course, for t equals 3, coming from the left side, we must show that the function is going towards the y value of -1. And so, again, you could have a closed circle here, you could have an open circle here. Really doesn't matter. In this case, since we have the jump discontinuity, in order for this to be a function, we have to have an open circle here, closed circle there. Our other option is to have open circle, open circle. But what we cannot have is closed circle, closed circle. Because if we have that, then by definition, we have not drawn a function. So those are things that have to be in place. So let's go ahead and move on to the next question. All right, so for question 8, this is similar to a previous question that we did. We want to know for what values of t this function will be continuous. So we just basically need to look at all the places where our graph has some kind of discontinuity in it and leave those t values out. So we're good from -infinity on to -2. So we got to skip -2, and we keep on going until we get to 0, because we have the jump discontinuity there. And then after that, according to what I have on my graph, I decided to have another jump discontinuity at t equals 3. So I have to exclude 3 from this, and then I go on to infinity, okay? Now, according to what you have drawn, your values of t may be different, okay? So for instance, you may not have from -infinity to -2. You may have wanted to stop your function right along here at when t is equal to -4. So in that case, instead of having a -infinity here, you would have a -4, okay? You may have wanted to draw some of this another way other than what I've done. Like for instance, you may have actually wanted the point to be defined here at when t is equal to 3, and after you come here, you just go up like that to where it's actually, excuse me, it's actually continuous at t equals 3. So here you just have from 0 to infinity. So those are some other possibilities there. So, but whatever you draw, just know that wherever you have your discontinuities at, that is where you need to exclude those particular t values. All right, so now let's look at questions 9a and 9b. So we say, suppose that f of x has a vertical asymptote at x equals 1. So what does this mean in regards to limits? Or put another way, we need to express what that is in limit notation. Okay. Now, for those of you that are actually taking my course, there is a page in your 10.3 or 10.4 notes that goes over this. And so on that page, what I have is a interpretation of what it means in terms of what happens on a particular graph, whether it's a vertical asymptote, a horizontal asymptote, function being continuous, so on and so forth, and how you express that in limit notation. I'm going to bring that up quickly so that we can kind of get a glimpse of that. And this is mainly for those of you that aren't necessarily taking my course, but you're looking at this video. If you need this to sort of help you to be able to interpret what it means to have a particular property expressed in limits, this may help you out. So I'm going to pause the video right now, bring that up, and then after that, we'll go back and answer these questions. All right, so quickly here, this is a summary that I kind of put together. I just hand wrote it and put it together to be able to say what types of limits you have and their interpretations. So if you start off, you see that for this very first one here, that if we have the limit of some function as x approaches a from both the left and the right, and we know that at x equals a, it equals that same real number, then we know that the function is defined there and is continuous there. So this is how we express continuity. And if you remember, I actually mentioned that earlier, I think within the first few problems of this particular video, if you've been watching since the beginning. So the second one here is how we say we have a jump discontinuity. We know that the limit of the function equals some real number L as x approaches a from both the left and the right, but we know that the actual defined point on the graph does not have a y value that is consistent with what the limit is. So in other words, the y value for the defined point isn't the same as what the limit's y value tends to go towards. And so this is how we know we have a hole. If we look here at our next one here, we see that if we take the limit of a function as x approaches a from both the left and the right, and we have a real number, but we know that the function is undefined at x equals a altogether, then that is what lets us know we have a hole in our graph. Okay. Now moving forward here, we have all the different cases of what we have when we have a vertical asymptote. And so in general, whenever we have the limit as x approaches some specific real number, and the answer to that is either positive or negative infinity, then we know we have a vertical asymptote. Now, 1, 2, and 3 are just here to give you all the different scenarios you could possibly have. So this first one that you see here is a scenario of whenever you have a function and you take the limit of it as x approaches a from both the left and the right, and the function goes towards positive infinity. This next one here is the same thing, but as the function goes down towards negative infinity. So you have the function on either side of the vertical asymptote either going up to positive infinity or down to negative infinity. Okay. In the next two cases here, you see that we're talking about the limit as x approaches some specific x value from the right. And so if you notice here, I'll only have the behavior of the function coming from the right side. And so, of course, this one is coming up, that one's coming down. And of course, this next one here is the behavior of the vertical asymptote only coming from the left. And of course, this first one here is coming from the left and going down to negative infinity. This next one is coming from the left and the function is going up to positive infinity. Okay, so that is what it would look like if we had a vertical asymptote. Coming down further, we see what our horizontal asymptotes look like with the two that are here with the star. Okay, And so as x approaches positive infinity for a function, if it equals a real number, then it will look something like this example, okay? And if it approaches negative infinity, then of course it'll look like this example, but it'll be on this side. For this next one here, what we're saying in this case is that the function does not have a horizontal asymptote as x approaches negative infinity as it goes to the left, but it does have one as it goes to the right, okay? So we can have functions that have one-sided horizontal asymptotes as well as those that have double-sided horizontal asymptotes. And we can also have functions to where the horizontal asymptote, let's say, may be y equals 0 going to the right, but to the left it may be y equals 3. Okay, so that is possible as well. So for the last ones here, the ones that have the asterisk by it, these are the other types of in behavior here. So, and I say that because whenever we talk about horizontal asymptotes, that is a specific case of in behavior where the in behavior is approaching a real number. So in the case of when the in behavior either goes to positive or negative infinity, like how we see when we have polynomials, then this is what it ends up looking like, okay? And so for number 4, this says the behavior of the function as x approaches positive infinity goes to positive infinity if we have something like this. Of course, 5 says, all right, if x is going towards negative infinity and the graph keeps going up, then it looks like this. And then, of course, for 6 and 7, you see that's kind of self-explanatory. X goes to positive infinity, y goes to negative infinity, and x goes to negative infinity, y goes to negative infinity for example number 7. And so when we're looking at the behavior of a function and we wanted to describe it in terms of calculus, in other words, we want to describe it in terms of limits, this is what you need to know. And so now that we know this, when we go back and look at that question, you're going to see that it's relatively simple to answer it if you know how to interpret what that particular property is that's being illuminated in the question, and you just express it in terms of limits. So now let's go back to the practice test. All right, so now that we see this, we know that whenever we're talking about a vertical asymptote, we know that we have to have the limit of a function as x approaches some specific x value equal either positive or negative infinity. So here we could write that the limit as x approaches 1 of f of x could be either positive or negative infinity, okay? And so that's all we have to write. If we want to get a little bit more specific, we could describe what the right side of the vertical asymptote would look like, and we could describe what the left side of the vertical asymptote would look like. And of course, since we're not being specific here, we can come up with anything. So let's say in this case, if I wanted my vertical asymptote to kind of go up to the right and down to the left, then I could say this is positive infinity, and over here I could say that's negative infinity. So that is an acceptable answer as well. The one that I have here is actually all that I need, but if you wanted to get a little bit more fancy, you can do that. Now, for the next question, now we're asked about horizontal asymptote. So of course, with the horizontal asymptote, we know that the limit of the function has to be going as x approaches positive or negative infinity. So in this case, we either say this, or as x approaches negative infinity, we would say it goes towards -5. And of course, that's all you need to do for that particular question. All you're doing is you're taking something that you learned from college algebra or pre-calculus, and you're translating what you know that particular property of a graph looks like in that language and just translating it into calculus language, which means you're going to use limits. All right, let's go ahead on to question number 10. All right, so question number 10 asks us, well, it tells us that the total cost in dollars of manufacturing X auto body frames is given by this cost function. And what we want to do is find the marginal average cost per unit at 2,000 frames. And we want to interpret this in everyday language. So the key to this is to understand what we mean when we say marginal average cost. So what we're given here is a cost function. Whenever we say average cost, which is denoted by having a line over our cost function, it is really just our cost function divided by x. So if we take what our cost function is and we divide it by x, we see that we get 60,000 divided by x plus 300 whenever we simplify. Okay, and to make life easier for us, we're going to write this 60,000 divided by x as 60,000 times x raised to the negative 1 plus 300 because of what we need to do next. So now what we're actually do is find the marginal average cost. So finding the marginal of anything is code for find the derivative or the rate of change of it. Okay, so here what we're going to do is say we want to find out what the derivative of the average cost is, essentially. And then we're going to take that and evaluate it at x equals 2,000. So, but we need to calculate this first. And so I'm going to rewrite this another way. So you can use either one of these notations here. But when we take the derivative of this, just like how we did before, if we use the power rule, we know we have the 60,000, and then we'll multiply that by a negative 1, and then we need to subtract 1 from the exponent. And of course, for any constant number, the derivative is always 0. So once we're done here, we have a negative 60,000 x raised to the negative 2, which is just going to be negative 60,000 over x squared. So now what we need to do is evaluate this at x equals 2,000 because x is auto body frames. So here I'm going to say it's 2,000 like that, put the line over it, and then do it like that. And so now all we have to do is plug in 2,000 into this particular function here. So say 60,000, negative 60,000 over 2,000 squared. And if we compute that, then that's going to turn out to be a negative 0.015. And of course, since this is cost, that's actually going to be in dollars. And since this is a derivative, we're doing dollars per frame. So if we wanted to interpret this, what this actually means is that if we are making auto body frames and our current cost structure is described as the 60,000 plus 300x, then what the marginal average cost is, or the rate of change of the average cost if we were to produce 2,000 frames at once, our cost is going down by 1.5 cents per frame at the moment that we're actually producing 2,000 frames. And so we're kind of looking at it as, all right, if we wanted to produce, let's say 500 frames within a particular production cycle, then that's what the cost would be. And then let's say we increase it to 1,000, and then we go to 2,000, like how this question is asking, and then we go to 3,000. And of course, our goal is to say we want to be able to reduce cost as much as we can, but for whatever reasons, we may have some other business constraints that keep us from having to be able to get it to where we have a maximum decrease in the amount of cost that we have for a particular set of frames because of whatever reasons. And so for this example, at 2,000 frames, for whatever reason they have to make it, so they need to know, all right, well, how much is our cost going up or down when we make that many frames within a particular production cycle or time period. Okay, so that is sort of the way that you do this problem, as well as the context behind it. Let's move on to question number E11. All right, so for question number 11, this is the question that I was referring to way early in the video about we had calculated, I think our function was this, and I had rewrote the function like this, and I said, all right, we know that dy over dx is y prime of x, and I was telling you that for that particular problem, all we had to do was y prime of x times dx. And the whole notion of this dy over dx is just a change in y over the change in x. And if we look at the limit of that, this meant the same thing as taking the derivative of the function, or the derivative of y with respect to x at a particular x value. And so we're going to use this to be able to approximate an incremental change. Okay. And so the reason why I was referring to all that is so that we can do this problem. So I'm not going to go over all those details again, but what I am going to do is explain how what we're using here can be interpreted for us to be able to use it as a differential approximation. And so you'll see how all this stuff ties together, hopefully. All right, so let me erase this and then we'll start the problem. All right, so we have a company and they're going to sell N units of a product after spending X thousands of dollars in advertising. And we know that they're tracking that relationship in between how much they actually sell and, well, the number of units that they sell versus how much they actually spend in dollars. And it's given by our function N. And so this is good as long as the amount of money that you're spending is in between $5,000 and $30,000. So our question says we need to approximately what increase in sales will result by increasing the advertising budget from $25,000 to $25,500. And we want to use a differential approximation. So when we say what is going to be the increase in sales, we want to know what the change in our N value is going to be, okay? And if you notice from what I had said before about the dy over dx thing, we could use delta N over, in this case, delta x to be an approximation of what the actual derivative of N would be with respect to x, or the rate of change. Or in the course, rate of change is also interpreted as the rate of increase or the rate of decrease, or if it's constant, we would say that as well. So here we know that dn over dx could be equal to that. However, since we're trying to get an approximation of this, if we rewrite this way, then an approximation of this could be done by saying, instead of having dx, which is theoretically the smallest change in x, we could do this, okay? And so the one thing that we need to note here that is implied, but I'm going to explicitly let you know this, is that when we do this approximation, we're doing this with everything being in respect to the first x value that we have here. And let me see if I can write that in. Now, what do we mean by that? We're talking about here is going to be our x1, here is going to be our x2. So this is the old x value, this is the new. Now, one of the things that we have to understand is that since x is in thousands of dollars, we're not just going to put $25,000 for x1 and $25,500 from x2. We need to translate that in terms of thousands. So this is going to be x2 minus x1, where x2 is 25.5 and x1 is 25. And of course, the difference in that is 0.5. So 0.5 K dollars, which is the same as $500. So now that we know what delta x is, the only other thing we need to know is what is going to be the derivative of our function here evaluated at x1, which is going to be 25. So let's find out what the derivative of our function n is going to be. And using what we've learned before, the derivative of 60x is just 60, and the derivative of x squared is just going to be 2x. And so now, if we evaluate this at x sub 1, which is the same as 25, then we just evaluate this by substituting 25 for x. We know that all this is just 50, and the difference in between 60 and 50 is 10. So now that we have this, we can come up with our approximation by just saying the derivative of n evaluated at x sub 1 is just going to be 10, and we know that our delta x here is going to be 0.5. So, of course, half of 10 is just going to be 5. And so what this tells us is that if we increase sales, well, if we increase advertising budget by $500, then what that's basically telling us that the increase in sales is going to be by 5 units. Okay. So it seems like for every $100 that we spend extra in advertising, we get another unit sold. So that's kind of how I would interpret it. And so that's what our answer means. All right, let's move on to question number 12. All right, so question number 12 says, what continuously compounded interest rate must an investment earn to grow in value from $125,000 to $370,000 in 18 years? So to know this, we first have to know what the continuously compounded interest formula is. And so we have a regular compound interest formula, and then we have one that is continuously compounded. So I'm going to list both so that you know the difference. So our regular compound interest formula looks like this. Okay? Where P is the principal, N is the number of times we compound per year, R is the annual interest rate, and T, of course, is time in years. And to go back to N being the number of times you compound a year, if you compound annually, then N is 1. If you compound semi-annually, then N is 2. If you compound quarterly, which means 4 times a year, then N is 4. If you compound monthly, then that means N is 12. If you compound daily, then that means N is 365, and so on and so forth. Okay. Now, for this problem, we will not be using this because this does not give us a quick way to be able to figure out continuously compounded interest. Or in other words, what is this as n approaches infinity? Now, theoretically speaking, we can actually derive the formula for continuously compounded interest, which is this, by taking the limit of the right-hand side of this function as n approaches infinity. Now, for what we need to know, that's kind of out of the scope of what we're studying. But just to let you know, when we take the limit of this side, or the right side of this function here, I just x'd out as n approaches infinity, and we do all the algebraic manipulation to it, we do actually end up getting this particular formula here. And so this is the one that we're going to use. So with that being said here, we know that the 125 is going to be our P, or our principal, or initial amount. Our A, or the new amount, is going to be 370,000. We know that our T is going to be 18 years. And since we're trying to find what the compound interest rate is, this is what we're trying to find, R. So we're going to plug in all this information, and then after that, solve for R. So we have 370,000 equals 125,000 e raised to the r times 18. Okay. And if we simplify this, first thing that we can do is divide both sides by 125,000. And so if we do that, we'll get 370 divided by 125 equals e raised to the 18r. All right, so if we keep on going here, we see that 370 divided by 125, that fraction will reduce to 74 divided by 25. And of course, we have equals e raised to the 18r. So from this step here, we need to change this particular exponential equation into a logarithmic one. And so there's a couple of different ways we can do that. I'm going to go with probably the most popular way to do it, which is just to take the natural log of both sides. So if we do that, then this is what it would look like. And of course, from here, if we move on, the left side is not going to change much, but we know here that natural log of e raised to the 18r, all this simplifies to just 18r. And it's because of a property of log base e of e raised to the x is just x. And so when we compare this, natural log is the same as log base e. And of course, when we have it like this, we're just saying that whatever's in the exponent is what this equals. So all of this is just 18r. And so we have this equal 18r. And of course, to finish up, we just take natural log of 74 over 25 and divide that by 18. And then of course, if we put that in our calculator to get an answer here, and I'll go ahead and put it in mine, see what we get. The answer that we get here, and I'm just going to write out everything, is 0.0602882927. And so, here, let me erase this right quick. So even though this is an approximation, this is what the calculator actually gave me. And if we approximate that in terms of percent, this is going to be about 6.03%. So we know over that 18-year period, to have your money of 125,000 go to 370,000, that would be about a little over a 6% return over that 18-year period. All right, so let's move on to the next question. All right, so for our next question, we're asked to find the marginal cost function when our cost function is 3,000 plus 100x minus x squared. And again, for this one, this is a relatively easy question. The key to this is understanding the language. So when you see marginal anything, you know that means take derivative. So what this is basically asking us to do is to take the derivative of this cost function. So if we start off here, the derivative of any constant is 0. The derivative of 100x is just 100. And the derivative of x squared is just 2x. So, of course, once we're done here and we simplify everything, I still can't draw zeros for some reason. So our final answer here is just 100 minus 2x, and that is what the marginal cost function is. And again, when we say marginal anything, what we're trying to do is track the rate of change of whatever it is that we're trying to model with our function. So let's move on to the next question. All right, so question number 14 asks us to be able to find out what the derivative of our function x squared plus x is using the difference quotient. Now, the one thing I want to make sure that you understand on this, regardless of whether you're taking my course or you're in another course, and they ask you a question like this. When you see using the difference quotient, what they're expecting you to do, and what I'm expecting you to do for those of you that are in my course, is I want you to actually compute what the difference quotient is, and then from that, take the limit of the difference quotient. What I do not want is this, where you come and say, all right, well, I know the derivative of f is just 2x plus 1, and that's all you give me. That's not what we're trying to see here. We're trying to see, can you actually evaluate the difference quotient get an expression, and then take that expression and evaluate it when h is 0. That's what we're trying to see for this question. So you may get the right answer, but this question is more so of how you got the right answer. Okay? All right, so now that we understand that, the first thing that we need to do is figure out what the difference quotient for this is going to be. So you need to figure out what all of this is going to be for our function. And so we start off by, this is f of x plus h. So everywhere where we see x, we're going to replace it with x plus h. Okay. Excuse me, y'all. Sorry about that. And so now we have minus, then we just need to do f of x. So we just have x squared plus x. And we take all that and divide it by h. Okay. Now, next step we're going to do is we're going to try to expand out what's here in this first grouping symbol. So we know when we do x plus h squared, that's just x plus h times x plus h. And when we multiply that out using the FOIL method, we end up getting x squared plus xh plus xh plus h squared. And then, of course, here we just have plus another x plus h. And then over here in our second grouping symbol, we need to distribute our negative to both terms there. So we'll get negative x squared minus x. And all of that will be divided by h. Okay. If we keep on going here, of course, we see that we'll have x squared plus 2xh plus h squared plus x plus h. And I'm going to drop the parentheses or the grouping symbols at this point because we really don't need them. Minus x squared minus h, all divided by h. All right, so at this point, this is a very pivotal point in this problem. And so once we have our numerator expanded out, whatever terms that do not have an h in it, they should be able to cancel out with another term in the numerator. So here we have x squared does not have an h in it, so it should be able to cancel out with this term. This term has an h in it, we leave it alone. This term has an h in it, we leave it alone. This one does not have an h in it, so we should be able to cancel that out with another term. This term has h in it, so we leave it alone. And so once we're done with that, now what we do is we rewrite everything else, and everything should have an h in it. All right, so when we rewrite everything, we'll get 2xh plus h squared plus h, all that divided by h. And here you can either form this into 3 different fractions and then reduce, or you can do like how I'm doing, factor out an h out of each term. And then we know that these h's reduce to 1. And we just have 2x plus h plus 1 as our result. So all that we've done at this point is figured out what the difference quotient is. Okay. Now what we need to do is add the limit notation as h approaches 0 to that so that we can actually find out what the derivative is. And so when you write this question, or when you're answering this, it must be written this way. So do not be lazy and do shorthand notation. It must be written this way. So now, if we want to find out what the derivative of f is, which is the limit as h approaches 0 of this difference quotient, here we know what our difference quotient is now. It just simplifies to 2x plus h plus 1. And so now, on our next step, we're actually going to execute the operator for the limit. And since for this operator limit, h is the variable for it, and we only have an h here, we're going to substitute 0 for h. And the reason why we're able to just plug it in is because in terms of this limit operator and h being the variable, this expression looks like a polynomial. And so we know that for polynomials, or in general, any function to where we can plug in a value that's a real number and we can get out something that is a real number or a real expression, we know that it's in the domain, so we're allowed to do that. The direct substitution property, for those of you that are wanting to refer to an actual theorem in the textbooks, the direct substitution property is what actually allows us to be able to do this. So here, of course, I just plug in a 0 and I get 2x plus 1. And so that is what the actual derivative of f is. And this is how it should look whenever you're asked the question of being able to figure out what the derivative of a function is in terms of the difference quotient. All right, so let's move on to the next question. Okay, so for question number 15, we see that we have the same type of question, but now our function is a little different. And so our function now this time is f of x is equal to square root of, and then we have 2 plus x under the denominator. So when we see our root functions like this, in particular the ones that are of even nth root, we have to approach evaluating the difference quotient a little different. And so what we're going to use here is the strategy of what's called a conjugate radical. And so in doing that, what we're going to do is take the numerator of whatever our difference quotient is, and we're going to take the conjugate of it and multiply our difference quotient expression by 1, but writing it as the conjugate of the numerator divided by the conjugate of the numerator. So in doing it that way, that's going to free up or release some of the square root signs that comes up in our original form of the difference quotient that actually allows us to be able to simplify it in the way that we need to. So I'm going to go ahead and just start writing out what our difference quotient would be in general. And then from that, you'll see how when we employ the conjugate radical strategy, how that's going to actually help us simplify everything. All right, so let's try that again. So we have f of x plus h minus f of x all over h. So here this would be square root of 2 plus x plus h, be all together like that. And then this will be minus f of x, which is just this, all that divided by h. And of course, here at this step, we know that there's not much we can do to simplify anything because we have the square roots right here. So what we're going to do is we're going to multiply this expression by the conjugate radical, basically taking this by 1 and doing it as square root of all this plus square root of that. So we're going to do that next. All right, so to do that, we're just going to say square root of 2 plus x plus h like this. And now instead of minus, we say plus. And we're going to do the same thing in the denominator. So we're just going to copy the same thing and put it down here. Okay, so now that we're done with that, then of course we need to multiply the numerators together and multiply the denominators together. So before we go and do that, one of the things that we want to notice here to kind of make this easy for us to do, notice that if we multiply the numerators together, this particular term here and that term are the same thing. So we can think of this as A, and this term here and that term here is together, so we can think of that as B and B. And if you notice, we're going to be doing A minus B times A plus B. In other words, we're going to be looking at this like that. If you remember, whenever we multiply two binomials like this, where one is minus, one is plus, then the outcome when we multiply all of these is a squared plus AB minus AB minus B squared. And of course, these two terms cancel to 0, and we just end up with A squared minus B squared. So we're going to multiply a numerator, and it's going to simplify to be something real simple, because we're essentially going to be able to get rid of these square root signs, because whenever we take the square root of something squared, that too didn't doesn't look too good there. So let's try that again. Do that squared, we actually end up with absolute value of x. Okay, and so in this case, because whatever values of x we will plug into this particular expression here, we know that from our original function that square root of 2 plus x, the domain of that, we have to set all this greater than or equal to 0, which means, let me do this a different way. Of course, if we turn that around, it would just look like this. And so that means x has to be greater than or equal to -2. So we won't be plugging in any values that are less than -2. And if we look here, the lowest value that we'll plug in is a -2. So the smallest value that we would get here in this particular term would be h, same as here. And the smallest value we would get inside of our radical here would be 0, which is all fine. And so as long as the values inside of our absolute value sign here, which is essentially what we'll be doing here, will be greater than or equal to 0, we can simply interpret the absolute value of x as just x, where x is assumed to be all values that are non-negative. So I'm saying all of this because when we do the next step here, we're going to be skipping a lot of steps because there's a lot of concepts in it. But what I'm explaining to you right now is those concepts. So I'm going to erase this, and then we're going to move on with the next step, and you'll see how everything simplifies. All right, so now that we have that together, we move down here. Then we know that when we multiply our first two terms together, that's just going to be square root of 2 plus x plus h, all of that squared, which would just give us 2 plus x plus h for the first term. And then minus, since we know that this is a squared minus b squared, and we're looking at these terms as b, then we know that all this just simplifies to 2 plus x. And so all of that will be over h times, and then we're going to write all this business here. We'll close off with that. And so now, in our next step, we're just going to distribute our negatives across both of those terms there. And please, whenever you're multiplying this, please be careful that whatever the second term is, since it's minus, make sure to put the parentheses around it all so that you remember to distribute. So we have 2 plus x plus h minus 2 minus x, all over same thing we had in the denominator last time. Okay, so now from here, we know that 2 and minus 2 cancels, and we know that x and minus x cancels, and we just have h left. So for moving on here, we just have h divided by h, and we'll rewrite the denominator again. And of course, these h's reduce to 1. And so now all we have is 1 over square root of 2 plus x plus h plus square root of 2 plus x. And so this is what our difference quotient actually is. So now what we're going to do is take that, and we're going to evaluate it by doing the limit when h is going to 0. So when we say this, we need to rewrite that. So therefore, the derivative is going to be the limit as h approaches 0 of f of x plus h minus f of x, all that divided by h, which is just going to be the same as the limit as h approaches 0 of what we see here. And so now you can see that because of our limit rules, one of our limit rules allows us to be able to evaluate the limit of the numerator divided by the limit of the denominator. And then also what we're allowed to do there is anytime we're taking the limit of an nth root function, we can slide our limit operator on the inside of that and then evaluate the limit on its own. So I'm saying all that to say that there's a bunch of limit laws that we can do to eventually get to what I'm about to write, which is this. So here, all this just equates to, we can just plug in 0 for h. Get rid of that. And then plus 2 plus x there. And then, of course, we see that all this will just simplify to square root of 1 over square root of 2 plus x plus 2 plus x. And of course, since we have 2 of them in the denominator, then that is what we write. And that would actually be the derivative of the function that we were given, which was square root of 2 plus x. That is the derivative of it by using the definition of the derivative, which is doing the limit of the difference quotient. And so I wanted to make sure that in this practice you saw the simple example of whenever you have a polynomial function and you perform the limit of the difference quotient versus when you do one of these with an nth root function, and particularly an even nth root function, where you need to actually employ the conjugate radical thing, or a conjugate radical strategy. All right, so let's move on to our last problem. And I thank you for hanging with me this long. I know this has been a long video, but I wanted to make sure that I do the best that I can to explain everything in detail so you not only understand how to get the answers, but you understand the actual thinking behind the answers. Okay, so that's why this video is as long as it is. All right, so our last problem. This problem asks us to solve this particular inequality using continuity properties. And we want to make sure that we explain the role of continuity here. So the first thing that I want to state is that at the heart of this problem, it really is just a college algebra or pre-calculus problem. And so the way that we interpret what we see here is what we're basically asking is for what values of x is this function x squared divided by x plus 2, for what values of x is it strictly above the x-axis. That's literally what we're asking, okay? Now there's several different ways we could do that. One way is, of course, we could just draw a graph of it and figure out for what x values is it strictly above the x-axis and then answer. The way that we want to go about it, though, is because we don't want to go through the trouble of actually drawing the graph, okay? We can, and those are skills that you learn in college algebra and in pre-cal, depending on what course you took. So you could do that, but we want to take the approach of using the test interval method, okay? But first we need to explain how continuity plays a role in all this. So if you see f of x here, you know that f of x is a rational function. And so one of the things that you learned about a rational function is that the only time that f of x will change signs, and what I mean by that is f of x is going to go from below the x-axis to above the x-axis, or above the x-axis to below the x-axis in 2 instances. And so that is when f of x has an x-intercept or when f of x has a vertical asymptote, okay? So I'm just going to write this down so that for those of you that need to visually see it, this will help you. So we want to say f of x changes sign, and that is to say f of x will go from below to above the x-axis, or above to below the x-axis when, and we got 2 situations here. Case number 1, when f of x is equal to 0, that means you have an x-intercept. And number 2, when f of x is undefined, but we have the behavior of the function as x approaches some value a, either equaling positive or negative infinity, which means you basically have a vertical asymptote, okay? So how continuity plays a role in this is that for case one, this is when the function is continuous and it changes sign. For case 2, the function is not continuous and it changes sign. Okay? And so I'm going to say it is continuous at some x equals a, and I'm going to say here that it's not continuous at some x equals a. So that's how continuity plays a role in this. And so whenever we are trying to figure out for what values of x is the graph of a rational function either strictly above or strictly below the x-axis, we use these properties that we know about a rational function in particular to be able to help us out. And so this is the reason why when you were in college algebra or pre-cal, whenever you were doing the test interval method that we're about to do, this is why we had to find out what our x-intercepts were and where our vertical asymptotes were. Because of, in terms of continuity, we're checking to see, hey, we want to know when it can switch from being above or below the x-axis, when the function is continuous and when it's not. And these are only 2 ways that happens. All right, so let's move forward here. And now let's go ahead and employ the test interval method. So doing the test interval method, we note that for our function, and I'll go back up here so that we can see it, we see that the zeros of the numerator are going to be where our x-intercepts are, and the zeros of the denominator are where our vertical asymptotes will be. So for the zeros of the numerator, for our x-intercepts, we know that x squared has to equal 0, and of course if we solve that, we know x is just 0. For our vertical asymptotes, we know that x plus 2, if that's 0, then x has to equal minus 2. So at -2 and 0, those are going to be our partition numbers on our real number line. And so we got -2 here, and we have 0 there. Now, since the sign that we have up here is greater than, then that means we cannot include x values for where the function is on the x-axis. So that means here at x equals 0, our graph is actually on the x-axis then, but we can't include that. Of course, at a vertical asymptote, we never include that. So I'm saying all that to say is that in those instances here, we're going to put an open circle around these values to remind us that we cannot include these values in our answer, okay? So here, when we write out our intervals, It's going to look as follows. I'm going to say from negative infinity to negative 2, and then from negative 2 to 0, and then from 0 to infinity. And so we're going to test all of these intervals using test values to see if it's going to be positive or negative, or put another way, seeing if it is below the x-axis or above the x-axis. Okay. So if we pick some test values here, we'll just randomly select some. All right, so if we randomly select some x values here, then I'm going to select, let's see, right here I'll select negative 3, and here I'll select negative 1, and here I'll select 1. So that way we have some values for each of the intervals that we need to test. All right, so now that we have that, let's just go ahead and plug it in and see what we get. So when f is evaluated at negative 3, we get negative 3 squared divided by negative 3 plus 2, which is 9, divided by negative 1, which is a negative 9. So we know our graph is going to be negative for this interval, which is not what we want, because that means that the graph is below the x-axis for these interval of x values. So let's keep on going. When f is negative 1, you know that's negative 1 squared divided by negative 1 plus 2, which will give us 1 divided by 1, which is 1. So that's positive. So this is telling us that the graph is above the x-axis then, so we do want that in our interval. So we know that the interval from negative 2 to 0, strictly in between, is going to be at least one of the answers. And then let's evaluate it at 1. And we see we get 1/3 here, which is also positive. So that means that the graph is also above the x-axis there. So our actual answer to this question, which is for what values of x is the graph strictly above the x-axis, well, that happens from all the values in between negative 2 to 0 to all the values from 0 to infinity. So this is your answer to this question. And so what we've done here is we've taken a concept from college algebra or pre-cal, asked it in this test, but try to put more meat around it by having you to understand how the role of continuity actually plays in being able to do a test interval method. So that's the point of the question. Okay. And so this review is a little longer than your actual exam, just so that you'll see all the different types of problems. For those of you that may not have done well on your first exam and you're wanting to retake, I still recommend that you look at this again, because this will be your way of sort of reviewing your first exam so that, your first exam, so that you'll be able to be prepared for the retake if you need to take that. All right, so again, thank you so much for hanging with me here. I know it's been a long time. Hopefully you took some breaks in between here, but again, I hope that the amount of detail I went into here will definitely help you understand the concepts in this course better, and that this will make you successful either on your first time taking this test or if you elect to retake this particular exam. All right, thank you so much. Take care, and check out some of my other videos.